Okay, one of the most practical manifestations of non-ideal gas behavior is something known as the Joule-Thomson effect, which is a key step in the refrigeration cycle. So we're talking refrigerators, air conditioners, and heat pumps. And there is a step in the refrigeration cycle known as throttling, and that occurs when a high pressure gas is is passed through a rather narrow opening or a porous plug. As it does that, the pressure drops rapidly. And so you end up here with a much lower pressure. It turns out that you'll also end up much colder, as shown on this diagram. So this is the throttle or the porous plug. This is where a large cooling happens. And that's known as the Joule-Thomson effect. Now, we should note that it only happens if we have a non-ideal gas. Because if it was an ideal gas, then as these particles spread out, they don't slow down at all. There's no change in the energy because they don't interact with each other. It's only because we have a non-ideal gas. And when we increase the separation distance between particles, we've got more electrostatic potential energy, therefore less motion energy, therefore it's colder. Because according to kinetic theory that we'll get to later in the course, temperature is proportional to how much kinetic energy the particles have. So here is a refrigerator, and it's got really only one moving part, the compressor, which pumps hard on the gas and increases its pressure, and then it passes through the condenser and loses some heat to the environment. Then it goes through the throttle valve, which is where it gets really cold through that rapid expansion, the Joule-Thomson effect. And then it goes through the food area where it absorbs thermal energy from the environment, warms up a little bit, then it gets pumped by the compressor again. And this is sometimes called the vapor compression cycle. Now, the refrigerant fluids that are in here are pretty nasty things and have lots of global warming potential. So these units are all sealed up, and it's not something that the average person is allowed to touch or open up in any way. We will have a demonstration of one of these systems that we can actually do some measurements on, and it's been properly set up for us by certified experts. What we can say here, and we'll just draw a little potential well, is that right here, before we entered this throttle valve, the particles might have had some average separation right here. So this is a graph of potential energy versus separation distance. Well, as they expand rapidly and the pressure drops, there is going to be an increase in the separation distance. Therefore, as we said above, there is now less PE, more PE, what am I saying? There's more potential energy on that graph. Because the potential energy has just gone up, right? It's gone from there to there, and therefore less kinetic energy, and therefore colder. Okay, so it's a non-ideal gas effect. It's very important and totally applied. So the practical uses of this effect are, as we already mentioned, refrigerators and air conditioners, something known as a heat pump, which is kind of a fridge in reverse. What we do there is we actually we pass this refrigerant outside, so it's very cold, and so it will absorb energy from the cold outside air. And then we bring it back into the house, and we dump the heat into the house. So it works on basically the same cycle. It's just where we had the food before, and we were absorbing energy from the food to keep it cold. Now we're absorbing energy from the outside air to bring it inside the house and warm us up. Okay, another place where this gets applied is in the liquefaction of gases, say to make liquid oxygen or liquid nitrogen. And there's a throttle there, and so there's a rapid expansion of the gas which cools it, and in this, some liquid will form and it'll collect here in the bottom of the container. Okay, now most gases cool upon expansion. Okay, when we have got to highlight that this is almost all gases. But some gases, and there's a couple of examples, like hydrogen and helium, at room temperature, they'll actually warm up. And there's reasons for that we'll go into later. But, basically we can just say that hydrogen and helium are actually about here, right? They're fairly small separation distance, and therefore, as they expand, as the separation distance increases, you're actually getting less potential energy and more kinetic energy, and that's why they warmed up. Okay, so where are we next? Ah, yes, the refrigeration cycle. And we have to introduce a quantity known as enthalpy. So let's consider a flowing gas, such as, well, it could be the steam in a power plant or a refrigerant in a cooling cycle. And so there's going to be a chunk of the gas here, or the fluid that's about to enter this control volume, and there's another chunk here that's about to leave. And so let's say this is P1V1, and this is at pressure 2 and volume 2. Now, the first law tells us that internal energy change is Q plus W. And the work, we're going to break up into several different terms, okay? Because, you see, the gas, in addition to doing work, say pushing, this is supposed to be a turbine blade in a steam plant, the gas will push on that and it'll do work. And so there's work out there. But in addition to that work, you've also got work being done on the gas by other parts of the gas. So you see, this element of gas, as it pushes in here, is going to compress this and do work on the gas. Okay, so as this little chunk of gas pushes in here at relatively constant pressure, we could say, what was the work done on the control volume? Well, the volume in the control volume will actually be decreasing as this moves in, decreasing by an amount V1. So we get that work done, positive work done, work in on the control volume, which makes sense. On the other end, as the gas in control volume pushes this one out of the way at pressure P2, which is relatively constant, the change in volume will be positive because the control volume gas is expanding into that space. And so we get that work is out in that case. So when we write the first law, then, we're going to distinguish between two types of work. We're going to distinguish between the internal work, which is the gas doing work, one part of the gas doing work on another part, or the gas doing work on itself, and the external work, pushing the piston or turbine. So this is what the first law looks like in that case. What we've just seen is that the internal work here is related to this quantity PV. Right? We had like P1 V1 minus P2 V2 for that term. And this is the change in internal energy delta U, so that'll be Q plus this, plus any external work that was done. But if we bring this over to the other side, then P1 V1, that's kind of like the initial, and this is kind of like the final. So initial minus final, if you bring it over to this side, then it's final minus initial, which of course is a delta. So what we're doing here is we're changing the first law, and we are just keeping the external work on this side, and any sort of internal work, we're bringing it over here with internal energy. And now we're going to define this as something different. We're going to call this enthalpy. And we're going to say that it only changes if there's Q or external work. It doesn't change for internal work. So this is a useful quantity. So, there's a nice spot to write that right there, isn't there? Okay, so we call this quantity enthalpy, just like that. So let's see, did I have it right down there? Yes, I did. There we go. Okay, so now, as we said, that delta PV, that's internal work, and then there's the external work. And enthalpy is only going to change if there is heat flow or external work done. So if there's only internal work, and this is going to be the case of flowing through a porous plug, then enthalpy will be a constant. Okay? Enthalpy is only going to change if we can say energy crosses the system boundary, either through heat flow in or out, or external work in or out. And the amount that enthalpy changes by will just equal the amount of heat flow in or out, or the amount of external work done. Now, enthalpy reflects the amount of energy required or available in a thermodynamic process. So in this case here, say you have a change where the internal energy is decreasing. So you'd say, okay, the internal energy of the system is decreased. There's clearly something that's going to be released, right? So final minus initial, 2 minus 5 is minus 3. So you might think you might have access to 3 units of energy. But of course, that gas actually did a little bit of work on itself, and so not a full 3 units of energy is released. What's actually released, the delta H, is the change in U plus PV, is actually negative 2. So the energy, the useful energy that you can get out of a thermodynamic process is the change in enthalpy. Because you can't control these internal works, right? That is just going to be part of the change. Now, we talked about enthalpy when we visited the thermal power plant, and we said there were 4 key points in the Rankine cycle. 1 to 2 was a pump, and when we pump it, there was external work in. So I should give a bit more room there for myself. So delta H there was the work that was done by pumping on that liquid. Now, from 2 to 3, we're traveling along an isobar, and in the boiler, there is a lot of heat flow into the gas. So again, the enthalpy is changing. From 3 to 4, we're in the turbine, and there, there's work output, and the work output is just the work that the gas actually does on the turbine. And then finally, from 4 to 1, we were in the condenser, and then there was a lot of heat that was out of the gas and into the environment. So there were changes in enthalpy at each stage, and we used enthalpy tables to figure out how much work was done by the pump, how much heat flowed in from the boiler, how much work was done in the turbine, and then how much heat was exhausted from the environment, and then ultimately we were able to come up with the efficiency using those steam tables. But what we're interested in now, at this point in the course, is the application of enthalpy to the study of the refrigeration cycle. So here's a picture of a porous plug, and the gas is about to push through this. So this has been compressed. This is a high pressure gas. But as it pushes through this porous plug, it's really just doing work on itself. There's only internal work. There's just delta PV work. And in that case, enthalpy, which we defined as U plus PV, is not going to change because no heat flowed in or out and there was no external work. So enthalpy is a constant for the throttling. And we will see that later on this other type of plot. This is actually a pressure enthalpy diagram, pH. And right here is the throttling process. It happens at constant enthalpy. And for the power plant, that was a temperature entropy diagram that was useful. Here, this is a pressure enthalpy diagram for refrigeration cycles. If we go through the stages then, first, heat flows into the fluid when it passes through the interior of the fridge. So where is that? Okay, so here it was throttled. Right here, there's Q in. So you can see there's tiny little numbers there. This is number 4 right there. So that was after the throttling. This is number 3 right here. So between 4 and 1, that's where it's passing through the food section and it's absorbing energy. So this is the thermodynamic fluid. Thermodynamic fluid is absorbing energy from the food that you put in there. Okay, so that's that step right there. So there is delta H because heat's flowed into the thermodynamic fluid, into the refrigerant. Then we do external work on it and we compress it. So between the points 1 and 2, this is the compressor and the enthalpy changes. And you can see the pressure goes way up. That's what the compressor does. So delta H in this case is due to the external work by the compressor. So the enthalpy changes. Next, heat flows out of the fluid when it passes through the condenser at the back of the fridge. Okay, so between points 2 and 3 here on the back, there's a network of wires on the back of your fridge, and there's a fan sometimes that will blow air over those pipes, over those tubes, to cool down the refrigerant and to transfer, it ends up transferring energy to the room. So there's Q out at the condenser. And then finally, we get back to this process here, right here, this constant enthalpy between 3 and 4 in the throttle valve, the Joule-Thomson effect that we want to talk about. We're going to spend about another class, 2 classes on this, just discussing this process. So we've just discussed the concept of enthalpy, and we've said that it's a constant for this process because the gas is only doing work on itself. It expands very quickly, the pressure drops precipitously, and it gets very cold. As a result of being very cold, it can absorb energy from the food. So what it remains to do at this point then is to actually try and come up with, for this cycle, how much cooling do we get? And that's embodied in a coefficient known as the Joule-Thomson coefficient. We're going to write mu JT. Mu, the Greek letter mu, and then JT for Joule-Thomson. It's actually that's supposed to be an equal sign, the temperature change with respect to pressure at constant enthalpy. And so this says, for a really big pressure drop, how much does the temperature drop? Okay, I guess we can write that in here. The change in temperature, the rate of change of temperature with pressure at constant enthalpy. And this is known as the Joule-Thomson coefficient. Now, it varies from gas to gas, obviously. Nitrogen and argon, those both cool down. Remember we said hydrogen warms up? It's actually got a negative coefficient. And we're going to try and figure out what sort of things this coefficient depends on. Let's notice where the sign change comes from. When we're expanding rapidly, the pressure is dropping, so that's a negative. If the slope was a positive, like it was for nitrogen, well, we know the delta P was negative. That would mean that the delta T is also negative in order to have a positive slope. So if the temperature change is negative, that means the temperature drops and it gets colder. That's why the positive coefficients like nitrogen and argon are actually going to cool under a Joule-Thomson expansion. What about hydrogen? So this is like nitrogen and argon. What about hydrogen? Well, pressure still drops in an expansion, but the Joule-Thomson coefficient is negative. That's, oops, I That's backwards, sorry. And the reason the slope's negative, well, the delta P part in the denominator, the dP is still negative, but the temperature change is positive. And that's an increase in temperature. It just got warmer. Now, this doesn't happen for very many gases, but we still do need to explain the effect. So if our Joule-Thomson coefficient is positive, that gas is going to cool down. If our Joule-Thomson coefficient is negative, that gas is going to warm up. Delta P is always negative. It just depends on what the sign of delta T is. And again, we can sort of explain that effect on this energy well. We can say that a gas like nitrogen or argon is typically here in terms of their average separation distance. So when they expand, there is more potential energy, therefore less kinetic energy, therefore it's colder. Hydrogen would be over here, and so as it expands, there's actually less potential energy, therefore more kinetic energy, so it got warmer. All right, so we'll have a look at equations of state and see how they affect the value of this Joule-Thomson coefficient. And we'll end up talking about something known as the inversion temperature as well, and that's the temperature at which you switch from cooling to warming up. So more on that when we get to class.